Okay, welcome to today's lecture. We'll continue our linear programming lecture under the operations research course. So in the last videos, we look at the graphical method of solving linear programming problems. So this lecture, we'll be looking at the simplex method. That's the first algebraic method of solving linear programming problems. So we will first open the whiteboard and we would take it from there. All right, so we have the whiteboard here. So the simplex method. So the simplex method. So by name, what I prefer to advise students is that the method is very simple and also complex at the same time, right? So it's called the simplex method. Now, so the simplex method is actually a method for solving linear programming problems, however, in an algebraic form, right? In an algebraic form. So it actually involves four main steps. It involves four main steps, right? So the first step is actually transformation of the general linear programming model into a standard form, or what we call augmentation. So when we're doing the graphical, we mentioned standard form, but that form is actually convert the inequalities into equation. But here we would transform the general LP problem or the LP model. Remember, when we had the LP model, we have the objective function and it's subject to various set of constraints, including the non-negativity rule constraint, right? So we transform the LP model into a standard form, right? Or what we call the augmentation, right? What we call the augmentation. So after the transformation, the second thing to do is to define the initial solution. So we then define the initial solution of the LP model. So the initial solution here is when we set the various decision variables. That's x1 to 0, right? And I is the number of decision variables we have, or which also make up the number of constraints, right? So we set the initial solutions in terms of the decision variables within the various constraints or the systems of constraints. We set them to 0, then we get initial solution. Then the third one, or the third step, is now we now search for a better solution. We search for a better solution, usually if any exists, right? Sometimes some don't exist, then you have to end it there. Then your initial solution becomes your final solution. So we search for a better solution. And this aspect of the search is actually the main simplex method. It's actually the main simplex method. Then 4, we actually repeat step 3 until a better solution is found, right? Until a better solution is found, or until we do not get any better solution, right? So we keep searching until a better solution that is found, right, remains the same solution and there is no, so a better solution is found and there is no better solution that can be found, right? All right, so we'll say that we can say that we will repeat the solution until no better solution is found or a better solution cannot be found. Let's put it that way. So you keep repeating this, the step 3, which is the search, until a better solution cannot, which is very important, cannot be found. So if it cannot be found, then at that point, the simplest process will say that it will terminate, and then the solution which is found is now termed the optimal solution, as we refer to in the graphical method. So there are several augmentation approaches that's peculiar to maximization problem or minimization problem. So we shall take the problem one after the other. So let's look at example and let's look at solving maximization problem. All right, so solving maximization problem. So let's assume that we have developed a model, right? And the model is said that we are maximizing a function z, right? And that function is 100 x1 plus 80 x2, right? And as usual, this function is subject to set of constraints. And the first one is 2x1 plus 4x2 is less than or equal to 80. 3x1 plus x2 is also less than or equal to 60. Then x1, x2 both obeys or satisfies the non-negativity rule, that is greater than or equal to 0. All right, so the first thing to do is to transform, remember the 4 steps, transform the LP model into a standard form. So we want to transform the LP model into a standard form. So what we do is that we employ algebraic method of solution, and therefore it entails as a solution of a set of simultaneous equations. So we are going to develop our inequalities into an equation form, but we'll call it a standard form. And the constraint inequalities will be converted into equations. We will introduce some parameters by adding slack variables. Like for instance, if it is a negative, if it's a less than or equal to inequality, then we add slack variables, right? And remember, is maximization, and we say with maximization, the LP model is such that all the constraints, the main constraints, are less than or equal to 0. Sorry, the right hand side. So the left hand side is less than or equal to the right hand side, right? And if it is minimization, is the opposite. The left hand side would always be greater than or equal to the right hand side. So that's why when we're developing the linear programming model, I tried to we tried to maintain this standard, right? All right, so if it's less than or equal to, you add slack, right? And so we will take our first constraint. So our first constraint is 2x1 plus 4x2, and it's less than or equal to 80, right? Okay, so what we do is that we add slack variable because of the less than or equal to sign, and therefore to augment this is 2x1 plus 4x2 plus a slack variable. Let's use s, and because we are introducing s for the first time, right, we will say x1. Right, sometimes we use the nomenclature or these variables just to help us to know where they stand, right? For instance, if it is in the first constraint, we can say that S1. If in the second constraint, we can say that S2, right? In that regard. So you just have to use any decision variable or any slack symbol so that you just remember where you are and where it will be, right, when you are referring to the solution. So that will still be equal to 80, right? So what this one means is that assuming x1 is equal to it attains any value, let's say 20, right, and x2 is equal to 0, right, then it means that 2 times 20 plus 4 times 0 plus s1 is equal to 80. So 40 plus s1 is equal to 80, and therefore s1 is equal to 80 minus 40, which is equal to 40, right? What this means is that the slack variable, we will later explain the meaning of the slack variable, but for now, let's assume it's a slack variable, right? Okay, so the slack variable in this case becomes an unused resources, right? Becomes an unused resources. So that's why we introduce the slack variable, so that if we find a solution for x1 and for x2, right, any solution that will still make up the 80, which is a resource. Remember, the right-hand side is the resource, the limiting resource or the available resource. Then the S1 becomes an unused resource, right? So that's why we introduce the slack variable. So let's take notice of this, which is very important for us. Then the second constraint is 3x1 plus x2 is less than or equal to 60. Again, because it's maximization, we add slack variable, and the second time we are introducing the slack variable, or we are introducing it in the second constraint, and therefore I use s2 to make this equal sign, and therefore it's 60. So this is a standard form, right? This is a standard form. Again, we can still test it and see. Remember, we said x1 is 20 and x2 is 0, right? That means that 320 plus 0 plus s2 is equal to 60. So that is 60 plus s2 is 60, and therefore s2 is 60 minus 60, which is equal to 0. What this one means that there is no unused resources, or all the resources for the second constraints have been used, right? So the slack variable actually do not contribute anything to the objective function, right? Because it's not a decision variable. Remember, the decision variables are what has been defined, the x1 and the x2, right? They are controlling the maximization function, that's the z, right? They are the physical product or the physical decisions that we are interested in. The amount of resources which are left unused will only help us to decide on several dynamics, right? So we will again take notice of this standard form here, right? And because the slack variables do not add any value, or they do not contribute to the maximization objective or objective function, or in this case, let's say profits or the revenue, or let's say the cost, right? So we would still include it in the objective function and give it a coefficient of 0. So it means that the maximization function z is equal to 100x1 plus 80x2. Because of the slack variable, right, the maximization function then becomes 100x1 plus 80x2 plus 0s1 plus 0s2. So this becomes our objective function, right? This becomes our objective function. So for us to do the transformation, which is the first step of the simplex method, you see that the objective function maximization function of z, which is 100x1 plus 80x2 plus 0s1 plus 0s2, right, is then subject to which set of constraints? The first one is 2x1 plus 4x2 plus our slack variable x is equal to 80, right? Okay, let's be is equal to 80 like that. Remember, I was saying that you have to arrange your write-up under each variable, right? It helps you to track how the decision variables flow, right? And when you are putting it into the next phase that we want to drive at, then you see the importance of doing this. Yeah, it's very important. Even when you are solving it using computational methods, it also helps. When you are even coding it in an advanced level, it also helps you to get a whole picture well. Now, the second constraint is 3x1 plus x2, right, plus our s2 here, right, is equal to 60. So you see how I do the alignments just so we know where they stand, right? Good. So in case you want to introduce the S1 in the second constraint, it can be 0s1. If in the first constraint, it can be 0s2. So it's actually not doing anything, but it's just trying to balance the entire equation in terms of the decision variables here are the same as the decision variables there, right? And again, our non-negativity rule applies to all the decision variables, even the ones that we have introduced, right? So this is how the standard form of the problem arises, right? This is how they arises. Now, after completing the first step, which is transformation of the general linear programming model into a standard form, then we need to define the initial solution, right? So the initial solution is actually defined using a tabular form, right? A tabular form. So the steps involved in the simplest method are conducted in the framework of a table, which is usually called Tableau, right? Called Tableau. So this contributes to computational simplicity, and it actually facilitates understanding of the entire process, right? So several formats of the Tableau are available. So when you look at several books, there are different forms of tableaus. However, they are mainly identical, and they will arrive at the same solution, right? Good. So the simplest tableau showing the various column and row and headings, right, will be provided here. So let's use this. Let me introduce the tableau here. So this is the kind of tableau we want to use. So we have that and that. So I have CJ here, I have CB, who will explain all this. I have the basis here, right? Then in the basis, we have ZJ and CJ minus ZJ, right? Then we have BI. Okay, I think I can get a ruler here. I always forget this. It should give me a straight line and change it to blue. Yeah, that's fine. So 1, 2, 3. Yeah. So we'll have this tableau, and we divide this according to the number of columns that we have, right? The number of columns and number of rows. So the number of rows are simply the number of constraints, right? And the number of columns are the number of decision variables per the objective function, right? And also the resources. That is the resources. So what we do here is that then we introduce our resources. Sorry, the decision variables. So the BIs are the decision variables, then the XIs are the resources. So the resources, the decision variables, we are X1, X2, S1, and S2. Remember, this is coming from, that's our new objective function, right? So this is column 1, column 2, column 3, and column 4, right? And the BIs are these resources, but we'll come to that later, right? So what are the coefficients that are sitting on left side of the X? So these are the coefficients, right? These are the coefficients. So we represent them here with coefficient for the first one, coefficient for the second decision variable, for the third, and for the fourth. So this is the tableau, right? This is the tableau. Now let's understand the various nomenclature that has been used here, right? So the CJ is actually the profit or the cost coefficient of the objective function. So if the objective function is a profit objective function, that is, we are maximizing the profit, then the CJ is referring to the profit. If we are minimizing the profit, or we are minimizing the costs, we won't minimize the profit. If we are minimizing the cost, then the CJ corresponds to the cost. All right, the CB is actually the same profit or cost coefficient of the objective function for the solution variable in the basis. So as we solve, the variables x and y, x1, x2, s1, s2, they come into solution. That is, they become the main decision variable that we are looking for, and they attain some values. The values will be in this area, right, which is the CJs or the CBs, right? So when is the CB, it means that is the coefficient of the decision variable in the basis, right, which is written correspondingly on the left, right? Good. So then we say that that's CB is the profit or is the cost coefficient of this decision variable, which is in the basis, right? Good. Then the basis actually is variables currently in the solution set. So the basis are the variables in the solutions. All right, then also we'll have the BI. So we'll fill this with this typical example and everything will be clearer, right? So the BIs, initially they are the right-hand side of the constraints, which are these, the resources, right? Yeah, which are these, the resources. They are initially the right-hand side, but during the iterations, they attain the solution corresponding to the decision variable, right? So during the iteration, they attain the solution values, right? Yeah, corresponding to the variables in the basis. Now the ZG is the decrease in profit associated with the production of 1 unit of each variable. So as we produce a variable, we use several costs to produce a variable. So the values that will be written here correspond to the decrease in profits associated with the decision variables, right? So with the decision variables, okay? Then the CJ and the ZJ is the unit increase in profit. The unit increase in profit if any of the decision variables is supposed to enter into solution, right? So it's fun when you are doing the iteration, and I'm hoping that we'll all catch it. So let's clean our Tableau, all right. And now let me use black and let's fill the Tableau, filling the Tableau. So usually, right, this is how to fill the Tableau. We pick these variables that we have, right? We pick the various constraints that we have. Okay, so now to fill the Tableau, right, we'll come back to our standard form. Our standard form model, right? So this is our standard form model. All right, I'm just taking the lines off, right? So when we come here, right, remember these are the CGs, C1, C2, C3, and C4. So we'll first do that. Let me take this off. So we'll first do that and say the C1 is 100, C2 is 80, S1 is 0, and S2 is also 0. All right. So then how do we fill this? The coefficient of the X1 in the constraint 1 is 2. And that for S2 is 4. that for S1 is 0. No, sorry, is 1. And that for S2 is 0. So we have to fill this. And remember, they are just 2 constraints. So therefore, we have 1, which is 2. This one is 4. S1 is 0. And S2 is, sorry, S1 is 1 and S2 is 0. Remember, we have it here. S1 is 1. For the second constraint, we have 3, 1, 0, and 1. So we'll come here and we'll say 3, 1, 0, and 1. Right? Good. Usually the slack variables form matrices. So just take note of that. Then we said the BIs are the right-hand side of the constraint. That is the available resources. So what we have here is 80 corresponding to the first constraint and 60 corresponding to the second constraint. So we have 80 and we have 60. All right. So what variables or the same variables must come into the basis? We say that they must come into the solution, right? Remember, in the graphical method, we said that if you have the graph and it's x1 and x2, right? X1 and x2, right? Usually at the origin here, right? X1 is equal to 0 and x2 is equal to 0. So we assume that for the first constraint where we have S1, 2S1 plus 4S2 plus S1 is equal to 0, right? If we are considering the initial solution, remember it's maximization problem, so the solution is moving away from the origin, right? But if we are considering the initial solution to be at the origin, then x1 is equal to 0, x2 is equal to 0. And if that happens, it means that we have 2, 0 plus 4, 0 plus s1 is equal to 80. And therefore, s1 is equal to 80. So s1 comes into the solution as the basis variable. So S1 will now be represented here, right? Yeah, we can also say S2 be represented here, but let's see that one as well. S2, the equation is 3x1 plus S2, x2 plus S2 is equal to 60. Again, at the origin, x1, so at the origin, x1 is equal to 0, S2 is equal to 0, and therefore 3 times 0 plus 0 plus S2 is equal to 60. So the surplus S2 is equal to 60. So unused resources. Therefore, S2 here will be equal to, will come into the solution or will be the decision variable, right? Good. Now, what is the coefficient of S1? The coefficient of S1 is 0. So you see, is 0 here. So that 0 becomes the coefficient of the basic variable, right? And coefficient of S2 is also 0. And that also becomes the coefficient of the basic variable for S2, right? So this is how we fill the table. Then here, we begin to fill this part of the table, right? The ZJ row, the ZJ row. So the ZJ row is obtained by multiplying this by that and adding it to this plus that, right? So 0 times 80 plus 0 times 60, and this one will be, I want to use a different color. This one will be 0, right? The same thing, we multiply 0 to 2, and we add it to 0 to 3, right? So 0 times 2 is 0, plus 0 times 3 is also 0. We do the same thing for the next row. Sorry, the next column. 0 times 4 plus 0 times 1, and that will be 0. We do the same thing, 0 times 1 plus 0 times 0. Then 0 times 0 plus 0 times 0 times 1, and that will be 0. So if I'm to make it clean, this is where I am, right? And this is Cj minus Zj, right? The Cj minus Cj, remember, these are the Cj's, C1, C2, C3, C4. And these are the Zj's. Sorry, Z1, Z2, Z3, Z4, right? So Cj minus Zj is simply 100 minus 0 is 100. 80 minus 0 is 80. 0 minus 0 is 0. 0 minus 0 is 0. So that is what we refer to as Cj minus Cj. Okay, so just trying to get rid of this extra marks here. Yeah. All right. So at this point, right, we need to start the iteration process. So the iteration process is such that you want to say that they are, how do a solution get into the solution basis, right? How do a solution get into the solution basis? So this is how it works. We look at the various columns and we find the largest Cj minus Zj. So the largest Cj minus Zj is this, right? Then we refer to that as the pivot column, right? What this means is that the corresponding decision variable, which is x1 on top here, right? The x1 on top here would actually enter into solution. So the x1 here will come and replace one of these, but we don't know which one it will replace. Right? Good. Then when we find this, then we use this and also that to find out which decision variable in the basis column. This is the basis column. In the basis column, this one, that must leave for x1 to come in, right? That must leave for x1 to come in. So we do a small computation here. So the computation that we do, so this pivot column is just indicating that X1 must enter into the solution. That's the basis solution. However, which one? S1 and S2, which one is going out? We call that row pivot row. Which one should be a pivot row? We don't know. What we do is that we divide the 80 in the solution, which is the BI. We divide it by the contributing value of the coefficients, right, in the decision variable. That's all we do. We divide and we find the corresponding values. So what we do is that 80 divided by 2 is 40, right? What some people do in some tableaus, they put it here, 80 divided by 2 is 40, and then 60 divided by 3 is 20, right? I think it would be better to do that. So when we do that, then we pick the least value, right? Remember the CJ minus ZJ, we pick the highest value. However, here we pick the least value. So the least value here is this value, right? So the pivot column, row is actually this row, right? We refer to as the pivot row. If you want to refer to it as a pivot row, you use the arrow entering and say pivot row. But if you use the arrow going out, you can just say out, meaning that that's decision variable S2 is going out of solution and is being replaced by X1. So here it can be in or pivot column. Here it can be pivot row. The arrow goes into the box or into the table like that. But if you want to use arrow going out, then you can just say out, right? Okay, so in that case, we can now erase everything, right? So when you do this, then you must circle your pivot number. So this is referred to as pivot number. It's the intersection of the pivot column, the pivot row, and the pivot column. I'm just extending this so that when I delete, I will just delete it once and for all, right? So the intersection between the pivot row, which is this one, right, and the pivot column, which is that, gives us the pivot number. So our pivot number is 3. I think that is clear. So I can delete these lines and make it more clearer. So this is why I extended it so that I don't delete any other thing. Yeah, I think this is clear. So now we know the entering decision variable, which is X1, and the leaving decision variable, which is S2, All right. So we have to now fill this tableau in the next tableau. So we have to create a new tableau here. I'm not sure we need this. It was just an illustrative purpose. I can delete all this, right? And bring our second tableau here. So the first tableau is always an initial solution, which is easy to be obtained, right? And the second tableau is actually based on the first tableau. All right. So the second tableau is, I think I can still use this. Yeah, let me draw a very beautiful tableau. And so we draw our tableaus. Yeah. Hopefully they won't be too much, but if they are too much, we'll just delete some. That's all. Yeah. So you should be able to remember how to draw these tableaus or these lines within the tableaus. All right. So let's use black and say still CJ, CB, the basis, the solution basis, the BIs, X1, X2, S1, S2. Okay, so that one is left ZJ, CJ minus ZJ. All right, so let me see if I can get rid of this. For you to get rid of this because it's a line. Okay. So I can now delete this section. Okay. Seems like my eraser is frozen. Okay, I can still leave it. I can leave it out, no problem. So this do not exist. All right, do not exist. Yeah. Okay. The eraser is working, but it doesn't work on these lines. That is strange. Okay, so let's leave that out. And let's say, so how do we do the iterations? These iterations are easy, but they are complicated. So you just have to follow and see how it goes. So we have our pivot number, which is the 3, right? So the new row is first to divide all the pivot row by the pivot number. The main reason is that we want the pivot number, which is 3 here, right? We want the pivot number to attain a value of 1 unit. So we divide everything. So remember the X1 is coming to solution. It's 100 here, it's 80, it's 0, and it's 0, right? So 100 is coming to solution. x1 as we place s2, right? So we divide, it was initially 60, right? So we divide the 60 by 3. x1 here was the pivot number. So 3 divided by 3. There was 1 here, so 1 divided by 3. S1 was, let's see the value of S1. Okay, so 3, 1, 0, and 1. So 0 divided by 3, and then 1 divided by 3, right? Good. So this is the row, the pivot row, right? This is the pivot row. So now how do we get the new row for the first constraint? The base is S1 is still in solution here, and the corresponding S1 here is 0. So we still bring our 0 here, right? The solution here was 80, right? We have it as 80. So the next value would always be, let's take it. It will be, so the new value here, that's question mark. The new value here is actually the old number, right? The old number minus the old pivot number minus the old number minus the old number that was here. The old number that was here was what? 2. And when we go up, we'll see that it was 2. So it's the old number minus, into brackets, the old times the new, right? The old times the new. This is our pivot number, right? So when we are generating the number within this row, that's the first constraint, the old number here is very important because everything is revolving around it. So it is the pivot number, right? So the new number here, which is BI for the S1, will be equal to the old number there, which was 80, minus the 2, which is the pivot number, times the corresponding 20. Where is the 20 coming from? 60 divided by 30 is 20. So this is 20. So the corresponding number. So let's do this quick and we'll get it. So 80 minus 40, and that is 40. So the value here will be 40, right? All right. Now the number itself is, now this number 3 divided by 3 is actually 1, right? So let's replace it with our 1, right? So the new number here, let me use this value, let me use green. The new number here, right, that must replace the 2, is again the old number, which is 2, which was there. So the old number is 2 minus the 2, which is the revolving point corresponding to this column, the initial pivot column, which is this. right? Which is the initial pivot column, right? Yeah, it won't be here. The initial pivot column times the corresponding one is 1, because it is 1, which is the new pivot number of the pivot row. So this one will be 2 minus 2 is equal to 0. So 0 will replace this value. Zero. I'm not able to delete this red. I don't know why. So let's assume the red doesn't exist. Okay. All right. Okay. So this value, the next one, okay, sorry. So I was saying that we are looking for this value, right? And this value can be obtained from the old value, which is 4, minus the 2, which is the revolving value or the pivot number, or the number on top of the pivot number, right, corresponding to the pivot number for that particular constraint, right, times the new value, 1 on 3, right? So when you evaluate this, it's actually 2 on 3, right? So 2 on 3, this will be 10 on 3. So let me replace this with 10 on 3. Okay, what's the next value here? This. What value goes here? The old value is this 1 minus the same 2 times the new value. 0 on 3 is actually 0. So we can replace this with 0 and 0. So this one will be 1 minus 0 and is equal to 1. So 1 actually comes here. The next one is this contributing value. This contributing value, the old value is 0. So it's actually 0 minus the same 2 times the new value 1 on 3, which is this 1 on 3. So this one will be negative 2 on 3. And negative 2 on 3, we'll use that to replace this. Right, yeah. So we complete our Z. Our Z is again, we go this direction. CB times the BI plus this times that. So this one will give us 2,000, right? Then the next one, CB times this coefficient, this times this contributing value, and that will be 100. 0 times this plus this times this, and that will be 100 on 3. 0 times 1, 0 times 0, and that will be 0. 0 times this, 100 times this, and that will be 100 on 3. That will be 100 on 3. So what value was here? S1. Yes. So 100 on 3, doing CJ minus ZJ. So 100 minus 100 is 0. 80 minus 100 on 3 is actually 46. 2 on 3. 0 minus 0 is 0. 0 minus that is negative 100 on 3. So now we find the entering decision variable. What we say is the pivot column. The pivot column is the most positive or the largest in the CJ minus CJ. So we can see it is that, right? And which of them will actually go out? We don't know. We have to divide the BIs and that, and we divide this and that, right? And we say we'll put them on the right hand side. So if we are to do that, then we are saying that, let me delete all this. So we are saying that 40 divided by 10 on 3, right? Let me do it. 40 divided by 10 over 3 is the same as 40 times 3 over 10, right? Then 20 divided by 1 on 3, which is actually 20 times 3. And this one will be 12, and this one will be 60. And we say we will pick the least value or the smallest value. So this is the smallest value. That means that this row is the pivot row, right? Or the arrow goes here and says out. So this is the pivot column, or we say the in, right? So X2 is going in, and we can see that S1 is going out, right? Good, S1 is going out. So we can take all this out and make it more beautiful. So our next tableau, we will just fill the next tableau with our new values. That's the iterations. So, okay, so you can see that the tableau is easy, but you need to just be careful, and also you have to understand it right. So let's look at the next table. Let's look at the next table. Where's my pen? Okay. So for the next table, okay, let me still use this. I know I had a hard time using this, but to still be okay. Okay, so the next table. Okay, I need to divide this wall, that, and the basis, then BI, X1, X2, okay, 4. Let's go. So we'll get used to how the tableau is filled with time. So don't worry. CJ, CB, this is the basis, this is the BI, X1, X2, S1, S2, the ZJ, CJ minus ZJ, and what are the coefficients here? 100, 80, 0, 0. All right, so we can go back and refer to this table. So 46, 46, 2 on 3 is the entering, and we said that is the pivot number. The 10 on 3 is the pivot number, right? And when we got this, it was the 12, which was actually entering which was the lowest value, and therefore X2 was entering the solution going to replace S1, right? So it means that we are going to get X2 here. Already X1 is here, and X1 is here. This is already 100. X2 is 80, right? As we said, X2 is 80. Now, when we work on the BI, we got 12, right? It's coming from here because we are dividing the 80 by the 10 on 3. Okay, we are dividing by 80 by the 10 on 3. Okay, we'll also divide. So we'll divide everything in this pivot column, pivot row by the pivot number, which is 10 on 3. So 40 divided by 10 on 3 is 12. 0 divided by 10 on 3 is 0. 10 on 3 divided by 10 on 3 is 1. So always the pivot number becomes 1 in the next iteration, right? Good. Now, 1 divided by 10 on 3. 1 divided by 10 on 3 is actually 3 on 10. So, yeah. Then 2 on 3 divided by 10 on 3. So 2 on 3 divided by 10 on 3 is actually 2 on 3 times 3 on 10. And that is 1 on 5 by Z. That is 1 on 5. All right, that is 1 on 5. Okay, 1 on 5. Yes, so here, I think we made a mistake here, right? We missed a sign here. So the solution was, the old number is 0. So 0 minus the pivot number, which is the corresponding pivot, which is 2. So is 0 minus into bracket 2 times the old number, no, times the new number here, which is this one, 1 on 3. That will be negative 2 on 3. So there is a negative here. Yeah, you need to look at some of these things. Yes, so here is negative 1 on 5. All right, as I said, operation research will train you to be a careful engineer. Now, the next iteration, right, we can delete this, so we can do our rough calculations there, right? Yeah, let's use blue so that it's different. So the old number here is 20, right? 20. So we said the new number here to fill this area is actually the old number, which is 20, minus the corresponding pivots number. Sorry, which one? X2. So here, the corresponding pivot number is this 1 on 3. Is this 1 on 3? So everything will be revolving around 1 on 3. So 1 on 3 times the new number. What is the new number? It's 1. The new number is 1. Yeah. Oh, sorry. So the new number is actually the new number here. It's 12. So this is the number we are looking for. So the corresponding new number is what we are going to use. Yeah, this is the fixed number, the old number. This is the pivot number, and this is the fixed number, which is 1 on 3, the old fixed number, which is this. So it will be 20 minus 3, which is 4, and this will be 16. So it means that here will be 16. The BI for the solution basis X1 is 16. Okay, now, what do we do here? The old value here is 1. The old value is 1. So is the old value 1 minus the 1 on 3 is still constant times the new value here, which is 0. And this one will give us 1. Very easy. Very easy. Yeah. Again, this one doesn't exist. Okay. Yeah, this one doesn't exist. I don't know why sometimes you can't delete this. Okay. Now, the old number is 1 on 3. So we are filling this area. Right. The old number is 1 on 3 minus into brackets 1 on 3 times the new number. One on 3 minus 1 on 3 times the new number is 1. The new number is 1. So it's 1 on 3 minus 1 on 3, and it's equal to 0. So here it's equal to 0. Right? Now, S1. What is S1? S1 is actually the old number there is 0 minus the 1 on 3 times what's the new number? 3 on 10. It's 3 on 10. So this one will be negative 3 over 30, right? Which is equal to negative 1 on 10. So here will be negative 1 on 10, right? Then for this particular value here, is the old number is what? 1 on 3. So let's delete this and let's get space here. It's 1 on 3 minus into brackets 1 on 3 times the new number, negative 1 on 5. Negative 1 on 5. And this one will be 1 on 3 minus plus 1, 5, 3, 15, right? And this will be bam, 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 bam. I think 2 on 3. So this will be replaced by positive 2 on 3. So we multiply 80 by 12 plus 100 by 16. And we are going to get 2560. 80 by 0 is 0. 100 by 1 is 100. 80 by 1 is 80 plus 100 by 0 is 80. 80 by 3 divided by 10, 8, 3, 24 plus 100 times negative 1 on 10, 24 minus that, 14, then 80 by that, 40, yeah, minus 80 on 5, 5, 1, plus 100 by this, so 80, 50, 85, plus 203, and boom, 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 boom. We'll get 24. Yeah, 24. So CJ minus ZJ will be 100 minus 100 is 0. 80 minus 80 is 0. 0 minus 14 is negative 4. 0 minus 24 is negative 24. So here, what is the largest? CJ minus ZJ? There is none. Since there is none, it means that a solution has been found. It means the solution has been found. The iteration stops. So what is the next iteration? Repeat until a better solution cannot be found. So we cannot find any better solution, and therefore this becomes our final answer. So x2, so the optimal solution, right? The optimal solution is observed when there is no positive value in the CJ minus ZJ, right? Rho, there is no positive value here, right? There are zeros that are corresponding to x1, x2, and this is very important. When the decision variable is in the basis or is in solution or is a basis variable. So when it's here, we refer to it as a basic variable, right? It's in the basic variable or the basic solution. If it's in the basic solution, or if it's in solution, meaning that it's a basic variable, the corresponding CJ minus ZJ is 0. So we can see this to be 0, this to be 0, right? If it's not in the basic, it's not a basic variable like S1 and S2, then they attain any value, right? Good. So the values in the S1 and S2 column imply that introduction of S1 into the basic variable, if we are to introduce this here into the basic variable, it's going to reduce this profit by -14, or it's going to reduce it by 14, right? If we introduce S2 here into the basic solution, it's going to reduce this 2560 by 24. That's what it means, right? That's what it means. So the simplex process will terminate and the optimal solution is found. So we'll say that the optimal solution is x1 is 16, s2 is 12. Our z, the function, the profit is 2560, right? And we have a surplus. S1 is 14 and S2 is 24. So that's what we do, right? So you can see that this iteration needs attention. You need to be careful when you are working on this, right? And you need to really take your time and work it out. So in summary, the simplest process for maximization will transform the problem into a standard form by converting all the inequalities into equations with slack variables. So you have to add slack variables. Then after getting the standard form, you set up the initial tableau. When you set the initial tableau, then you determine the non-basic variable which is entering the solution. That is the pivot column. That is the most positive value of the Cj minus Zj, or the largest Cj minus Zj value. Then you now determine the leaving basic variable, which is the pivot row. So you now compute the new tableau row values, check whether the solution is optimal by checking the Cj minus Zj, whether there is a most positive value there. If not optimal, go to the step 3, repeat it, and follow the iteration process. And I think that's when, if any solution cannot be found, then we will say that we have attained the final solution. All right, I think this example is good. Our next example, we'll look at the minimization problem, where we subtract the slack variables. We subtract the slack variables and add an artificial variable. So on this note, thank you for being with me, and we'll meet in the next lecture. Thank you.